Okay, so I think we're squared away as far as that is concerned. Okay, so let me come back down to the PowerPoint. So the last time we were here, we were, talking about precipitation reactions. And the next topic we're going to talk about is that of oxidation and reduction. So let me define these terms first. So basically, whenever we have a reaction where there's a transfer of electrons from one atom to another, we call that a redox reaction. Redox is basically an abbreviation for reduction and oxidation, all right? So that is what characterizes these types of reactions. You have the transfer of electrons from one atom to another. So therefore, in terms of the actual definition of the individual terms, oxidation is what happens when you have an atom losing an electron in a reaction, and reduction is taking place where there is a gain of electrons by an atom in a reaction, all right? And there is a mnemonic that is used very often to help us to remember these definitions, like that I like to share with my students. Oil rig, right? So that stands for oxidation involves loss of electrons, reduction involves gain of electrons. So I hope you find that helpful in terms of remembering which is which, all right? Okay, so that's basically what oxidation and reduction is all about. And what you're gonna learn, excuse me, excuse me, 1 minute. I'm sorry about that. And what you're gonna learn, among the many things that you're gonna learn in this section, is that you cannot have one without the other. If you have oxidation taking place in a reaction, then reduction must be taking place, all right? Because if the electrons are being transferred, the electrons will have to leave from some atom to another atom. So you cannot have oxidation without reduction, all right? I want to also introduce to you this concept of what is known as the oxidation state, or in some textbooks, they call it the oxidation number. And it's basically an indicator of the extent or the degree of oxidation of an atom in a substance, all right? And the oxidation states are represented by oxidation numbers, as I said before. And there are some rules that we can use to determine the oxidation state of any atom in a particular substance, all right? So here's another definition of the oxidation number or state, which is probably more accurate. It is the charge the atom would have in a molecule or an ionic compound if the electrons were completely transferred, all right? So that's another definition that you can work with in terms of what an oxidation number is. So what we're going to do is go through these rules for determining the oxidation numbers of different atoms in a particular substance or in substances. And these rules you don't need to memorize word for word, but you do need to know how to use them. And I'm going to show you maybe 1 or 2 examples of how we use these rules to determine the oxidation numbers of atoms in a compound or an element. So the first rule is very simple. As you can see here, it says free elements that are not combined with anything, right? So they basically exist by themselves. In those states, the oxidation number of the atoms would be 0, right? So it doesn't matter what the element is. It could be sodium, beryllium, potassium, lead, hydrogen, even polyatomic molecules such as phosphorus. The oxidation number of the atoms in each of these cases would be 0, all right? So that's the first rule. The second rule is that when it comes to monatomic ions, the oxidation number is the same as the charge on the ion. So for example, in the case of the lithium plus ion, the oxidation number is +1. In the case of the iron 3 ion, the oxidation number is +3. And in the case of the oxide ion, the oxidation number or oxidation state is -2. So when it comes to monatomic ions, whatever the charge is, that is also the same as the oxidation state or the oxidation number. The third rule deals specifically with the element oxygen. And it says the oxygen, when it is combined with other substances or other elements, usually has an oxidation number of -2, with the exception of peroxides, where the oxidation number of oxygens in those compounds is -1. All right. So this rule here, and unfortunately, I neglected to include the fact that oxygen has to be combined with some other element. So that is something you have to keep in mind. If the oxygen is combined with some other element like hydrogen, sodium, whatever, then the oxidation number is usually -2 with the exceptions of peroxides, right? In the case of peroxides like hydrogen peroxide or anything containing the peroxide ion, the oxidation number of oxygen is -1. All right, so that rule is specific for oxygen. Okay, some other rules. Hydrogen. The oxidation number of hydrogen when combined with other elements is almost always equal to +1, excepting, and this is very important, excepting if the hydrogen is bonded to a metal in binary compounds. In these cases, the oxidation number of hydrogen is -1. So if hydrogen is combined with non-metallic elements, the oxidation number is +1, but if it is combined with metallic elements, then the oxidation number is -1. All right. Then we get to rules concerning group 1A, group 2A, and fluorine. So in the case of group 1A metals, when they're combined with other elements, the oxidation number is +1. When it comes to group 2A metals, the oxidation number is +2. And fluorine is always -1. So it doesn't matter what fluorine is combined with. If it's combined with some other element, then it's always -1. The only exception is if fluorine is combined with itself, in which case it's 0, right? But if fluorine is combined with hydrogen or sodium or aluminum, it doesn't matter. The oxidation number of fluorine is going to be -1. And then it says here for rule number 6, the sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge on the molecule or ion. All right. So what this rule is saying is that if you have a molecule or a polyatomic ion, and you add up all the oxidation numbers of all the atoms involved in that particular species, then the sum of the oxidation numbers will be equal to the charge on the molecule or the ion. Now, if it's a molecule, obviously the charge would be 0, there will be no charge, so therefore the sum of the oxidation numbers of all the atoms involved would be 0, all right? But otherwise, if you're dealing with a polyatomic ion, then the sum of the charges or the sum of the oxidation numbers will be equal to the overall charge carried by that polyatomic ion. So based on these rules, we can pretty much determine the oxidation number of pretty much any element in a particular compound. So for example, this question says, is asking for the oxidation numbers of all the atoms in the bicarbonate ion, HCO3-, right? So based on the rules, we know that oxygen is going to be -2 in terms of its oxidation number, because that's one of the rules that we saw on the previous slide. And we also know that hydrogen has an oxidation number of +1 because of rule number 4, right? So the question now becomes, what is the oxidation number of carbon? Well, we don't know that directly, but we can calculate it because of rule number 6. Rule number 6 says the sum of the oxidation numbers of all the atoms in a molecular ion is equal to the charge on the molecular ion. So we know that the sum of all the oxidation numbers of all the atoms in this ion would be equal to -1. So we can set up an equation where we take the oxidation number of oxygen, which is -2, and multiply by 3 because there are 3 of them. And we add to that the oxidation number of hydrogen, which is +1, plus the unknown, which is the oxidation number of carbon. And that set that sum to be equal to -1. And then all we have to do is solve for the unknown. And according to my calculations here, the oxidation number of carbon in the bicarbonate ion is equal to +4. So that's basically how that is done. And that's how you can determine pretty much the oxidation number of any atom in a molecule or ion. All right. Okay. So with that said, let's talk about redox reactions. These reactions where we have the actual transfer of electrons from one atom to another. So basically, as we said before, there is a transfer of electrons from an atom to another in a redox reaction. And we can also identify redox reaction in terms of the oxidation number changes that takes place for specific atoms in the reaction, right? So another way of looking at oxidation and reduction is that when something is oxidized, the oxidation number of that particular atom increases. And when an atom is reduced, that means that the oxidation number decreases. And the increase in oxidation number corresponds to a loss of electrons. The reduction in an oxidation number will correspond to a gain of electrons, all right? So you can see here that we can look at redox in terms of either increase or decrease of the oxidation number or gain or loss of electrons. Okay, so as an example of a simple redox reaction, I want to show you this picture here. So this picture is showing you a cylinder which contains a solution. And that solution is copper 2 sulfate, all right? And this coil that you see inserted into that solution is magnesium, all right? And if you set this up, put the magnesium in the solution of copper 2 sulfate, and you let it sit for a while, eventually you're going to observe two things. The first thing you'll notice is that the blue color of the copper 2 sulfate will be clearing up, right? So if you let it stand for a long enough period of time, it will actually become totally colorless, right? Another thing you'll notice is that you're going to see some metal deposits on whatever is left of the copper coil, whatever is left of the magnesium coil that is inserted into the solution. So those are two things you'll observe. And those two observations are due to an actual redox reaction that is taking place. So what I'm going to show you now is the equation for the reaction, and I'm going to show you how we know it's a redox reaction. So the reaction here is between copper 2 sulfate, aqueous, plus magnesium, solid, right? And the product of this reaction will be magnesium sulfate, aqueous, plus copper solid, all right? So as I said before, the original solution of the copper 2 sulfate, the color that is blue, all right? And the magnesium sulfate, which would be formed in the aqueous solution, is colorless, all right? So that's the reason why we see the solution become more and more colorless as the reaction progresses. Now, remember I said that there will be a deposit that would be left on the remaining magnesium that did not react. And that deposit will be the copper solid that is formed, all right? So this is the overall equation for this reaction. Now, what I'm going to do is derive the net ionic equation. And if you recall what we did the last time, we basically determined which of the compounds will dissociate completely. And if you recall, we said that any ionic compound that is in an aqueous solution will dissociate completely. So the copper 2 sulfate here will dissociate to form Cu2 plus SO4 2 minus. And these two would be aqueous ions. So that's aqueous. And this is aqueous. Plus magnesium solid. And then on the product side, you're going to have Mg2 plus aqueous plus SO4 2 minus aqueous and Cu solid, all right? So this would be the ionic, this should be Cu solid, all right? So that would be the ionic equation. Now, if you remember, to get to the net ionic equation, we cancel out the spectator ion, which in this case would be the sulfate ion here and here. So the net ionic equation would be Cu2 plus aqueous plus Mg solid to form Mg2 plus aqueous plus Cu solid, right? So this is where you're going to see that this is a redox reaction, because if you look at the oxidation number changes as you go from reactant to product, you see that in the case of the copper 2 plus, the oxidation number changes from +2 to 0. So that means that there's an increase in the oxidation number, right? So therefore, that means that this is oxidation that is taking place. And we can also look at it in terms of loss of electrons, because going from, or gain of electrons, I should say, because going from the copper 2+ to the copper solid, you're gaining 2 electrons. So we're gaining 2 electrons. All right. And then now, if you look at the changes as far as the magnesium is concerned, you see that going from, oh, my bad, I made a mistake here. This is not an increase. This is a decrease in the oxidation number from +2 to 0. So let me change that right here. My mistake. So this is decrease, a decrease in the oxidation number. And then in the case of the magnesium, there'll be an increase in the oxidation number because the oxidation number increases from 0 in the case of magnesium to +2. And this corresponds to a gain of 2 electrons. All right. So this is how we know it's a redox reaction, because the copper 2+, I'm sorry, I made another mistake. This should be loss of 2 electrons. I'm having my wires crossed this morning. So this would be loss of 2 electrons. Okay, so this is how we know that this is a redox reaction, because we have the transfer of electrons from the magnesium, which is losing 2 electrons, to the copper 2+, which is gaining the 2 electrons, right? And as a result, the magnesium will form the Mg2+, and the copper 2+, when it gains the 2 electrons, form the copper solid without any charge, right? So that's basically how this works. Another thing I want to point out here, and this is going to be true for every redox reaction that you'll be working with, is that for every redox reaction, the total number of electrons lost must be equal to the total number of electrons gained, right? That is true for every redox reaction without exception, right? Whatever the number of electrons lost in the oxidation part of the redox reaction would be equal to the number of electrons gained in the reduction part of the redox reaction. And that is true right across the board without any exception. And you're going to see how important this is when it comes to balancing redox equations, all right? There's one more thing I want to show you, another way of representing the redox changes. Let me lasso this here and delete it. Okay, so what I'm going to do is write down, what we call half equations to show you the oxidation and reduction taking place. So as far as the magnesium is concerned, Mg solid is oxidized to form Mg2+ as a result of the loss of 2 electrons, all right? And in the case of the copper 2+ ion, that will undergo reduction by gain of 2 electrons to form the copper, right? So we call these half equations, right? So this is the oxidation half equation, and this is the reduction half equation. And if we add these 2 equations together, then basically, just like we did before when it comes to, where did we do this? I don't think we did it before, but anyway, whenever you're adding 2 equations together, what you have to ensure is that the common items on both sides will be canceled out, which in this case would be the 2 electrons here will be canceled out with the 2 electrons on this side. And therefore, when you write down what is remaining, that would be the net equation, which would be Mg solid plus Cu2 plus aqueous to give you Mg2 plus aqueous plus Cu solid, all right? And again, this will become important as you're going to see in the examples that we're going to look at when it comes to balancing equations, because what you're going to see is that in order for us to write down a balanced redox equation, you have to ensure in one particular step, that the number of electrons lost in the oxidation process would be equal to the number of electrons gained in the reduction process, all right? Okay, So, any questions about what we have discussed so far with respect to redox reactions? Because it's very important that you understand all of this here before we move on to actually balancing redox equations. So, any questions about this? Any questions?
No question.
Okay. All right. So let me move on now to discussing balancing redox equations, right? So the thing about balancing redox equations is that if you try to balance equations like this in the traditional sense, you know, the way that we have been accustomed to, where we make changes to coefficients and on both sides and monitor the number of atoms of each element on both sides as you go along. For a certain more complex redox equation, that would be a very arduous task, very difficult, almost impossible in most cases, right? So there's another method. In some textbooks, they call it the Ion Electron Method, which is very systematic, very step by step, where if you follow the steps, you should have no issue in terms of coming up with the final answer in terms of the balance equation, all right? So what I'm going to do is go through the steps using a particular example. I'm going to go through it slowly so that we all can follow. And then we're going to go into some other examples, all right? So this is how we go about balancing redox equations. So the first thing here, we're going to use this example, a reaction where Fe2 plus is oxidized to Fe3 plus by dichromate in an acid solution. Now, I will admit that in this case here, not enough information is given. You're going to need one more piece of information in order to come up with an equation for this. And I'm going to add that information here. And the information I'm going to add here is that Cr3 plus is a product, all right? So you may want to make a note of that, all right? So basically the original question is going to be Fe2 plus is oxidized to Fe3 plus by Cr2072 minus, with Cr3 plus being a product of this reaction, right? So basically, based on that information, you are to determine the balanced redox equation, all right? So, give me 1 minute here. Okay, so first thing you need to do is write an unbalanced equation for the reaction. So basically, you're going to write, basically what you're going to do at this stage is identify the reactants and the products, and basically in the balanced equation, you're going to put the reactants on the left of the arrow, and you're going to put the products on the right of the arrow. So this is what you're going to end up with, right? So this would be the balanced equation right here. Fe2 plus the dichromate ion to give you Fe3 plus and the chromium 3 ion, all right? Then the next step is that you're going to separate this equation here into two half equations, right? So one half equation would be the oxidation half equation, where the Fe2 plus is converted to the Fe3 plus, right? And then the other half equation is where the reduction takes place of the Cr272 minus, which is being reduced to the Cr3 plus, all right? So that's the second step. You separate the equation into two half equations. Then the next step is that we balance the oxygen and the hydrogens. Now, the way we balance the oxygens, let's deal with the oxygens first. And I probably should have split step 3 into 2 steps, but let's go with this. So we balance oxygens by adding water molecules to the side with the fewer number of oxygen atoms, right? And we make sure that we add enough water molecules to that side so that the number of oxygen atoms on both sides will be the same. So for this half equation here, you'll notice that you have 7 oxygen atoms on the left side here, and there's none on the right side, all right? So basically what you need to do is, which is what is being shown here, I don't know if this is clear enough for you guys. Can you guys see these equations right here?
Yes.
Okay, so so to balance oxygens, we add 7 water molecules on the right side, because by adding 7 water molecules on the right side, we're adding 7 oxygen atoms on the right side, which balances with the 7 oxygens on the left side, right? So the oxygens are balanced, right? And then now to balance the hydrogens, what we do is that we add hydrogen ions to the side, which is deficient in hydrogens, again, to balance the hydrogen atoms on both sides. So you'll notice that there are 14 hydrogens here, 7 times 2, 14 hydrogen atoms total on the right side. There are no hydrogens here on the left side. So what we do is that we add a total of 14 hydrogen ions on the left side to balance with the 14 hydrogen atoms on the right side. Now, as far as the other half reaction is concerned, strictly speaking, you should be doing the same thing. But you'll notice, let me go back to the previous page. You'll notice that in the case of this half equation here, there are no oxygens and there are no hydrogens. So therefore, there's no need to balance any of those atoms. So therefore, we don't need to make any changes as far as that is concerned. However, if there were hydrogens or oxygens in the oxidation half reactions, we basically have to do the same steps. We balance the oxygens by adding water to the side that needs it, and we balance the hydrogens by adding H+ ions to the side that needs it, all right? So let me skip now to the 5th step. And this is where students tend to make errors. So let me go through this particular step slowly. So step 5 says you're going to add electrons to one side of each half equation to balance the charges on the half equation, all right? So basically what this step involves is the addition of electrons. Now, key thing you need to remember is that each electron carries a negative charge. Each electron carries a negative charge. So therefore, if you add electron to one side of a half equation, you will be reducing the total charge of that side by 1, all right? So that's a key thing you need to remember. So let's apply this particular rule to the balancing of this equation right here. So before you added the electron here, you would have +2 here on this side and +3 here on this side. So what that means is that in order to balance the charges, we need to add 1 electron to the right side, because by adding the 1 electron here, you're reducing the total charge here by 1. So the total charge on this side will be +2, which balances with the +2 charge on this side. Now for the second half equation, which is, let me go to my pen function here. For the second half equation, which is this equation right here, right? You'll notice that the total number of charges on the left side here is 2 times +3, which is +6. And the total number of charges on the right side would be 14 plus charges minus 2, so that would be +12, right? So we have +6 on the right side. We have a total of +12 on the left side. So the question now becomes, to which side would you add electrons and how many electrons would you add? Remember I said that whenever you add an electron, you would add, by adding the electron, you're reducing the total charge on that side by 1. So therefore, in this case here, I would add 6 electrons to this side here, because by adding 6 electrons to this side, you'll be adding -6 to +12, and that will give you +6, which basically balances with the +6 on the right side. So basically, the resulting equation, half equation, as a result of adding the 6 electrons will be what you see there, which is this equation right here, all right? So now that we have balanced the atoms, chromium, hydrogen, oxygen, and ions, and we have balanced the charges, then the next step is very important, and it alludes to what I mentioned before. If necessary, equalize the number of electrons in the 2 half equations by multiplying half equations by their appropriate coefficients. And that's important because if you remember, we said that in every redox reaction, the total number of electrons lost must be equal to the total number of electrons gained, right? That's true for every redox reaction. So in this particular case, we have 1 electron shown here to be lost, and we have 6 electrons here, which is gained, right? So the question now becomes, how do we ensure that the number of electrons lost and gained are the same? And as stated here in step number 6, what we need to do is to multiply one or both equations by certain coefficients. And in this particular case, that would mean that you'd have to multiply this entire equation here by 6, because by multiplying this by 6, you're going to end up with 6 electrons here, which would be the same as the number of electrons gained here. So the result of multiplying that equation by 6 will be this right here, 6Fe2 plus to give 6Fe3 plus 6 electrons, all right? Okay, so after that, the final step is you now will add these two equations together, right? And if you remember, I said before, whenever you do something like this, whenever you're adding equations together, you have to cancel out items that are common to both sides. And in this case, obviously, what is common to both sides are the 6 electrons, right? Which must be the case, because again, the number of electrons lost and gained must be the same. So therefore, these electrons must be canceled out. So you cancel those 6 electrons, and all you have to do after this is write down what is left. And that should be the final answer, right? And that's basically how you go about balancing a redox equation. Now, what I would strongly recommend that you do at this stage, even though this should be the final answer, what I would strongly recommend that you do at this stage is to do a final check through to make sure that everything is balanced, including the charges, right? So let us do that right now. So let's start off with the hydrogens. You have a total of 14 hydrogens on the left, and you have 14 hydrogens, 7 times 2, 14 hydrogens on the right. So the hydrogens are okay. You have 2 chromium atoms on the left, 2 chromium atoms on the right, so that's okay. You have 7 oxygen atoms on the left, and you have 7 oxygen atoms, the 7 here, multiply that oxygen. So therefore, you're going to have 7 oxygens here. So the oxygens are balanced. You have 6 iron here, 6 irons here, and then we have to check the charges to make sure that they're balanced, right? So if you add up 14 plus charges minus 12 minus 6 times 2, according to the calculation here, that's equal to 24. And if you do a similar calculation on the right side, 6 times 3, 18, 18 plus 2 times 3, 6, so 18 plus 6, that's 24. So therefore, the charges are balanced as well. So therefore, this equation is now balanced. Now, this last line we won't be concentrating on in this course here, right? So what this last line is saying here, step 9, it says for reactions in basic solutions, we add OH minus to both sides of the equation for every hydrogen ions that appear in the final equation. We won't be doing that. So in other words, all the redox balancing that we'll be doing will be focused on acidic reactions, right? Acidic solutions, right? We won't be concerned with basic solutions. I think that should be best left up to, Chem 2. In Chem 2, you'll be doing more of this. And at that point, you'll be able to learn how to carry out the same process, but for basic solutions, all right? So that's basically the steps involved in balancing redox equations. Okay, so I want to do a couple more examples, but before we do that, are there any questions? Any questions you guys have concerning balancing redox equations? Or this particular example?
No questions right now.
Okay, so I'm just going to come up with a couple of examples, and these are examples that I've completely made up, and I don't even know what the final answers will be, so this should be interesting. All right, so let me get out of this here. And let me go to my writing. My writing pad. Okay, so the first example I'm coming up with here is CrO4 2 minus plus SO3 2 minus to give Cr3 plus SO4 2 minus. Okay, so that's what you're given. And typically when you're given a problem involving balancing redox equations, this is something that you'll be given, right? And your task is to balance it. So if you recall, the first step in this process is that we separate this into 2 half equations. So the first half equation would be CrO4 2 minus to give Cr3 plus, and the second half equation would be SO3 2 minus to give SO4 2 minus, all right? So that's the first step. The second step, and to be perfectly honest, I don't think we mentioned this. Let me check something here. I just realized something. Or maybe I did, and I just don't remember. Oh, I skipped over it. Step number 3. It says balance atoms other than oxygen or hydrogen. I don't know how I missed it. So basically, if you, I forgot to mention that because you have 2 chromium atoms on the left side here, we need to multiply the 2 here, the chromium here by 2 to balance the chromium. So that's step number 3. Step number 3 says you need to balance atoms other than oxygen or hydrogen in each half equation. And that's basically what we need to do in this case. But in this case, however, actually we don't need to do, because you'll notice here that there's 1 chromium atom here and 1 chromium atom here. So that's okay. We have 1 sulfur atom here and 1 sulfur atom here. So that's okay. So typically what you'd have to do is balance those atoms, all atoms other than oxygen or hydrogen, right? So after that is taken care of, then we need to balance the oxygens by adding water to the side that is deficient of oxygen. So in the case of the first half equation, we have 4 oxygens here on the left. We have no oxygens on the right. So that means that we need to add 4 water molecules on the right to balance the oxygens. In the case of the second half equation, we have 3 oxygens on the left, 4 oxygens on the right. So that means that we need to balance the oxygens on the left by adding 1 water molecule on the left, all right? So that's how we balance the oxygens. The next step is that we need to balance the hydrogens by adding hydrogen ions to the side that needs it. So what that means for the first half equation is that on the right, we have 8 hydrogens, and here we have none. So that means that we need to add 8 hydrogen ions on the left. And then in the case of the second half equation, we have 2 hydrogens on the left. We have none on the right, which means that we need to add 2 H+ ions on the right. Then we get to the charges. And again, this is where students tend to make their mistakes. So in the case of the first half equation, the total charge that we have here is +8 -2, which gives you +6. And on this side here, we have +3. So that means that to balance the charges, we have +6 on this side, +3 on this side. So that means that we need to add 3 electrons to that side, all right? Just checking something here, 8 -3, that's 5 -2 gives you +3. Okay, right, so we add 3 electrons to the left side. Now for this half equation here, we have a total of -2 charges on the left, and here we have a total of 0 charges on the right, so that means we need to add 2 electrons here on the right, okay? So the next step is where we have to ensure that the number of electrons lost and gained would be the same. Now, let's see what the state of affairs is right now. As it is right now, we have 3 electrons here on the left of the first equation, and we have 2 electrons here on the right of the second equation. So the question now becomes, how can we ensure that the number of electrons lost is equal to the number of electrons gained? And in this case, the answer is that we need to multiply this equation here by 2. And when we do that, we're going to end up with 6 electrons plus 16 hydrogen ions plus 2 CrO4 2 minus to give you 2 Cr3 plus 8 H2O. And then for the second half equation, that means you have to multiply by 3, right? And in this case, the result of that would be 3 H2O plus 3 SO3 2 minus to give 3 SO4 2 minus plus 6 H plus. All right, and then we add these up. Oh, plus 6 electrons, can't forget that. All right, then we add these up. Of course, as I said before, when you're adding equations like these, we have to cancel out those items that are common to both sides, which would obviously mean that the 6 electrons here and here will be canceled out. But there are some other items as well. For example, there are 6 hydrogen ions here, and there are 16 hydrogens ions here. So what that means is that these 6 hydrogen ions here will cancel out 6 of these 16, leaving behind 10, right? And then you'll notice that you have 8 water molecules here and 3 water molecules here. So what does that mean? That means that these 3 water molecules will cancel out 3 of these, leaving behind 5, all right? Okay, so let's write down.
Professor.
Yes, sir.
Oh, really quickly. There's 5 lines in total. On that third line, why did you add 2 electrons to the?
Okay, very good question. So why did I add these 2 here?
Yeah.
Okay, very good question. So if you recall, I said on the left side here, the total number of charges here would be -2. Whoops.
Yeah.
Right, the total number of charges here will be -2. On the right side, the total number of charges here, before adding the electrons, the total number of charges here would be -2 plus 2, which would be 0. Right?
Oh, okay, I see. All right.
So therefore, in order to achieve balances in terms of charge, we need to add 2 electrons to the right side so that the total charge here would be -2, which balances with the -2 on the left.
I see. Okay, I wasn't multiplying the 2 and the H plus.
Yes, right.
I was thinking it was -1.
Right. Okay, and that's a very good point to raise. Yeah, the charges, like for example, what you just said, this plus charge here will be affected by the 2 here.
Yeah.
Okay. That's something that you really have to take into account as well. All right. Okay. So I hope that clears up that particular problem.
Yes. Thank you.
Okay. So where was I? Okay. So we canceled out the electrons, we canceled out the water, we canceled out the hydrogen. So basically what we need to do is write down what is left. So what is left would be 10H plus 2 CrO4 2 minus plus 3 SO3 2 minus, and I think that takes care of everything on the left side. And then on the right side, we have 2 Cr3 plus 5 H2O plus 3 SO4 2 minus. And I think that takes care of everything on the right side. Okay, so that should be the final answer. Again, as I said before in the previous example, I would strongly recommend that you do a quick check through to make sure that everything is balanced. So let's start with the hydrogens. On the left side, we have 10 hydrogens here. On the right side, we have 5 times 2 10 hydrogens, so that's okay. On the left side, we have 2 chromiums here and 2 chromiums here on the right side, so that's okay. On the left side, in terms of the oxygens, we have 2 4s 8, 8 plus 9, so 8 plus 9 gives you what? That's 17, right? So that's 17 oxygens on the left, and over on the right, we have 5 plus 3 times 4, 12, 17 oxygens, so the oxygens are okay. And then for the sulfurs, we have 3 sulfurs here, 3 sulfurs, so the sulfurs are okay. And then we have to look at the charges. So as far as the charges are concerned, we have plus 10, minus 4, 2 times minus 2 minus 4, minus 6, 3 times minus 2 gives you minus 6. So that gives you what? 10 minus 4, that's minus, that's, what am I saying? 6 minus 6, so that's 0. And then let's look on the right side. We have plus 6. There's no charges from the water, but we have 3 times minus 2 from the sulfate, so that's minus 6. So that would be equal to 0 as well. So the charges are balanced. So therefore, this here would be the final balanced equation. All right. Okay, any questions about this? Any questions?
I do have a question.
Yes, sir.
Why again did you multiply by 2 and by 3? Those
good.
two.
Okay. So the reason why is because for every redox reaction, the number of electrons lost in the oxidation process must be equal to the number of electrons gained in the reduction process. That is true for every redox reaction, right? Now, when we got to this stage right here, we ended up with 3 electrons being gained here in the reduction equation. And here we have 2 electrons here being lost in the oxidation half equation, right?
Yeah.
So therefore, obviously, those numbers are not equal. So when we get to this stage, what we need to do to ensure that this number is converted to something which is equal to a number that would be gained here is that we need to multiply this number here or this equation here by 2 so that we end up with 6 electrons here. And we multiply this equation here by 3 so we end up with these 6 electrons here so that they will cancel out. All
I
right?
see. Okay, that makes sense. Thank you.
There's a term in math. I don't remember. It's been a while since I've done math. You multiply, I think the term is highest common factor or something like that. I don't remember the exact terminology, but you have to find, basically you have to find a number that you multiply both equations by so that the number of electrons that is lost here will be equal to the number of electrons gained here. But you have to remember also, and this is another common error that students tend to make, you have to multiply that equation in its entirety by that number, not just the number of electrons. So like in this case here, we want to get 6 electrons here, but you have to multiply the entire equation by 2 in order to achieve that. So all these coefficients here will be doubled, right? So the 3 becomes a 6, the 8 becomes 16, the 1 here becomes 2, and so on and so forth. And the same is true when you multiply this equation by 3. All the coefficients in this equation here will be tripled. So that's why you end up with 3H2O plus 3SO32 minus, and so on and so forth. All right. Okay, so I hope this is clear for you because what I want to do now is another example. And this time I want you guys to tell me what to write down. So is it okay for me to get rid of this?
Yeah.
All right, so let me eliminate that. Okay, so here's another example. And again, this is one that is completely made up. So I don't know what the final answer is going to be. Okay. All right, so based on the examples that we have looked at so far, what would be the very first step?
Separate them into 2 half equations.
Okay, very good. So what would be the first half equation?
Mn and Mn2 plus.
MnO4 minus going to Mn2 plus.
Oh, I didn't.
Right. And the other one would be what?
CH4 and CO2.
Okay. All right, very good. What would be the next step?
Separate the equation. Then, wait, never mind. Balance the atoms.
Okay, so balance all atoms excepting oxygen and hydrogen, right?
Yes.
So in this case, we have 1 manganese here, 1 manganese here, so that's okay. In this case here, we have 1 carbon here, 1 carbon here, that's okay. So we don't need to make any changes there. So what would be the next step?
Do we count the charges?
Nope. Before that, we're going to get to that eventually, but there are at least 2 steps before that.
We balance the number of oxygens and we make the oxygens on each side equal.
Okay, so how do we achieve that?
Well, we have 2.
We have 4 oxygens here.
4 oxygens.
And we have none on the right side. So what do we add? And to which side do we add it?
We add it to the right side, 4 H2O.
Okay,
molecule.
very good. So you're going to add 4 water molecules. So let me do that right here. 4 water molecules. Very good. Okay. What about the second half equation?
We'll add 2 H2O molecules to the left side.
Exactly. And the reason for that is because we have 2 oxygens here, right?
Yeah.
So that means we're going to need 2 oxygens on the left side. So that means we add 2 water molecules. Okay. So far, so good. What's the next step?
We add the electrons to each side.
Nope. You're skipping over one important step. After balancing the oxygens, the next step would be to balance what?
Balance the hydrogens.
Okay, very good. And how do we do that?
You'd add 4 hydrogens to the left side.
Well, more specifically, you're going to add, and of course, you're talking about the first half equation, right? So more specifically, you're adding 4 hydrogen ions, right?
Ion.
So remember, it's hydrogen ions that you're adding, all right? But you're right, you're going to add them to the left side, all right? What about the second half equation? To which side would you add the hydrogen ions and how many?
You'd add it to the right side. And you
Okay.
would add 6 hydrogen ions.
6?
No, 8 hydrogen ions.
8, because on the left side, you have 4 plus 4. 2 times 2, 4, right? So here you're going to add 8 hydrogen ions on the left side, on the right side, I'm sorry. Okay, good. So now we get to balancing the charges. And again, let me remind you, students almost always slip up on this part. So I want to see if you guys know what to do in this case. Now remember, you're balancing charges by adding electrons, right? So, and also remember, each time you add an electron to a side, you're reducing the net charge on that side by 1, all right? Okay, so for the first half equation, to which side would you add electrons and how many would you add?
Huh. Well, do we count the number of electrons in each first?
Well, you have to count the total number of charges on each side. So what's the total number of charges on the left side here? Oh, by the way, I just realized something. I made an error.
Okay.
The error is right here. Can somebody tell me what the error is? This is incorrect. That should not be 4. That should
8.
Exactly. That should be 8. Okay, so let me clear that up. I'm glad I picked up on that error. And sometimes this is what happens. You have to kind of reevaluate what you did just to make sure. Okay, so 8 here. Okay. So, and that's very important because of the number of charges that we need to calculate. So what's the total number of charges on the left side here?
Is that 7?
8 plus charges minus 1, so that's plus 7, right? What's the total number of charges on the right side here?
Is that just 2?
Plus 2. Okay, very good. So now that we have identified the total number of charges, to which side would you add electrons in order to make sure that the total number of charges on the left is equal to the total number of charges on the right?
Would you add 5 to the right?
Exactly. 5 electrons to the, not to the right, I'm sorry, to the left.
To the left?
Yeah. And the reason why, and that's a common error students tend to make, they tend to add charges to the wrong side. If you add 5 electrons to the left, that means that you're going to reduce the charges here, the net charges here, from plus 7 to plus 2,
okay.
which balances with the plus 2 charge here. If you add 5 electrons to the right, that becomes minus 3, which will not balance with the plus 7 on this side. So this is not correct. All right?
Okay.
Okay, what about the second half equation? What's the total number of charges on the left here?
0.
0, exactly. What's the total number of charges here on the right?
1.
Huh? Hint, hint.
Oh, no, 8, my bad. I'm sorry.
Plus 8, all right? Okay, so again, the question is, to which side would you add electrons and how many?
You would add 8 to the right?
Exactly. Because by adding 8 electrons, you reduce the total net charge on the right side to 0, which balances with the 0 on this side. Okay, so let me just erase this here just to make some space. So what's the next step? What's the next step?
We combine them together.
But before you do that, there's something you need to do. Very important step. I mean, all the steps are important, but
you want to make the electrons on each side equal. So you
okay.
multiply.
Okay, go ahead.
You multiply them. You want to multiply the top part by.
You want to make the number of electrons here and here equal, right?
Yeah. So you
Okay.
multiply top by 8.
Multiply this one by 8.
Yeah.
Okay, let's do that. Let's do that first. So 8 times 5 gives you 40 electrons. Wow, I didn't know that these big numbers would result. You see, that's what happens when you just create problems. Okay. That's 64 plus 8 MnO4 minus to give 8 Mn2 plus 8 times 4, that gives you 32 H2O. All right. And then you multiply this one by what?
8 times 5 times 5.
Okay. Times 5. So that becomes 10 water molecules plus 5 CH4 to give 5 CO2 plus 5 8 40 H plus. All right. Okay. And then what do we do next?
Now we cancel out.
I'm sorry. I forgot the electrons. Plus 5 8 40 electrons. My bad. Okay. So what do we do next?
We cancel out the.
Okay. So we're going to add these. And as you just said, we cancel out the common items. Of course, that means the electrons will go. What else? What else will cancel out?
The number of H2O molecules.
Okay, let's look at that. So we have 10 water molecules on this side, and we have 32 on this side, right? So what's going to happen is that these 10 will cancel out 10 of these, leaving behind 22, right?
Yeah.
Okay. Anything else will cancel out?
Hydrogen atoms.
Ions.
Yeah.
Right. Okay. So we have 64 here. We have 40 here. So that means that these 40 will cancel out 40 of these, leaving behind 24, right?
Yeah.
And we just simply write down what is left. So what is left is 24 H plus 8 MnO4 minus plus 5 CH4 to give 8 Mn2 plus 22 H2O plus 5 CO2. And that should be the final answer. But again, as I always say, check to make sure everything balances out. let's start off with the hydrogens. We have 24 hydrogens here, plus 5 fours 20. So that's 24 plus 20. That is 24 plus 20. That's 44 hydrogens, right? And over here, we have 22 times 2, 44 hydrogens. So that's okay. We have 8 manganese here, 8 manganese. So that's okay. As far as the oxygens are concerned, we have 8 times 4, that's 32 oxygens. And here we have 22 plus 5 times 2, 10. So 10 plus 22, 32 oxygens. So the oxygens are okay. And then now for the hydrogens, we have 24, I'm sorry, not the hydrogens, the charges, my bad. We have 24 plus charges minus 8. So 24 minus 8 gives you 24 minus 8, that's 16, right? And here we have 8 times plus 2, 16. So the charges are balanced as well. So this would be the final correct answer. Okay. We have gone beyond the normal 50-minute that I would normally stop at. So we're going to take a break here and get back in the next 10 minutes, all right? And then I think what we'll do is just do one more example, maybe 2 more examples, and then move on to chapter 5, all right? Okay, so in the next 10 minutes, Okay, I am back. All right, so is it okay for me to get rid of what we have here on the screen?
Fine by me.
All right, let's, oh, you know what? Let me do this. All right, so I want to do another example. So I'm going to write down this unbalanced equation, C2O4, 2 minus, plus ClO3 minus to give CO2 plus Cl2. All right, so what would be the first step?
Separate them into two half equations.
Okay, so what would be the half equations?
C2O4, 2 minus, and CO2.
Okay,
And the second one would be Cl3 and CO2.
okay. Cl2, I'm sorry. Cl2, okay. What will be the next step?
Balancing the charges?
Nope. We have like 3 more steps before we get to that.
Balancing the number of oxygens on each side.
Okay, before that.
Oh, balancing the number of carbons.
Okay, balance the carbons. We have 2 here and we have 1 here, right? So how do we balance the carbons?
Do you add a carbon, or do you multiply?
Multiply by 2. Okay. And down here, we have 1 chlorine and 2 chlorines here. So we balance the chlorines by putting a 2 there. All right. Okay. So remember that important step. That was the step that I missed when I introduced this topic earlier. You balance all atoms excepting oxygen and hydrogen in the traditional way. All right. The next step is what?
Now we balance the oxygens, yeah?
Okay, so we balance the oxygens by?
Adding H2O molecules.
Okay, so let's look at the first half equation. How many oxygens do we have on the left?
4.
Okay, and how many do we have on the right?
2.
Nope. 2 times 2.
Oh, 4.
Right, so the oxygens are balanced already. So therefore, we don't need to do anything to that one, right? We don't need to make any changes. We don't need to add any water. Now, in the second half equation, how many oxygens do we have total on the left?
6.
Okay, very good. And how many do we have on the right?
0.
Okay, so how do we balance the oxygens?
We add 6 to the left.
Nope.
6 to the right.
Exactly. All right. Okay, so what's the next step?
We figure out the electrons.
No. We have to balance something first before we balance the charges.
You balance the hydrogens.
Okay, very good. So what does that mean for the first half equation? What does that mean for the first half equation?
For the first half equation, well, there's no hydrogens in the top.
Exactly. So we don't need to do anything there, right?
Yeah.
What about the second half equation, however?
In the second half, we have 12 on the right, so we need to
Okay.
add 12 on the left.
Okay, very good. 12 hydrogen ions. Remember, it must be hydrogen ions, right? Okay. Then we balance the charges. All right. So how do we balance the charges for the first half equation? How many charges do we have total on the left side for the first half equation?
2
Well, not just 2, -2.
-2.
All right. And how many charges do we have total on the right side for that half equation?
0.
Okay, very good. So what does that mean? To which side would you add electrons and how many?
Add 2 to the left.
2 to the left, you sure about that?
No.
Think about it. If you add 2 electrons to this side, you're going to be adding another 2 negative charges, which gives you -4, which will not balance with the 0 on the right side. So it cannot add 2 electrons to the left. Let me erase that here.
So 2 to the right.
Yeah, 2 electrons to the right. Exactly, because if you add 2 electrons to the right, you're adding a -2 charge here, which gives you -2, which balances with a -2 on the left. So the answer is you add 2 electrons to the right. So that's that. Okay, what about the second half equation? How many charges total do we have on the left? Let me make this more presentable. There should be a plus charge here. Okay, so how many charges total do you have on the left side for the second half equation?
Is it 10?
Plus 10, exactly. Because you have 12 plus charges -2. And how many charges do you have total on the right side?
0.
Okay, very good. So the question now is, to which side would you add electrons and how many would you add?
You would add it to the left side.
How many?
10.
Exactly. So you're going to add 10 electrons to the left side. Okay, so what's the next step? Let me erase this here. What's the next step? Let me give you a little hint.
You make the charges equal, the electrons equal, I mean.
Right, the number of electrons equal. So how would you achieve that in this case?
By multiplying the top by 10
By
and
10?
the bottom by 2.
Well, you could do that, but to make life a bit easier, what I would simply do is multiply this by 5.
Oh, by 5, okay.
Because that will become 10, and that is 10 already.
Oh, true.
You see what I'm saying? So
yeah,
that will make life a lot easier. So if you multiply the top one by 5, you're going to get 5 C2O4, 2 minus, to give 10 CO2 plus 10 electrons. All right? So these 10 electrons will cancel out these 10. And I don't think there's anything else to cancel out. There are no hydrogen ions on the right, no water molecules on the left. So all we have to do now is write down what is left, which would be 12H plus 2ClO3 minus plus 5C2O4 2 minus. And then on the right side, we have Cl2 plus 6H2O plus 10 CO2. And that should be the final answer. But again, let's check to make sure everything is balanced, starting with the 12 hydrogens here, which balances with the 12 hydrogens here. We have 2 chlorines here, 2 chlorines here. And then for the oxygens, we have 6 plus 5, 4 is 20. So that's 26 oxygens on the left. And here we have 6 plus 20, 26 oxygens on the right. And here we have 10 carbons. Here we have 10 carbons. And then we have to look at the charges. So here we have plus 12, minus 2, minus 10, and that's equal to 0. And over here we have no charges whatsoever. So therefore, this would be the final equation, balance equation. Okay. Any questions about this example? Any questions? Any questions?
I have none.
Okay.
Questions?
All right. Now I'm going to show you an example which is a bit different from what we have looked at so far. And let me just write the unbalanced equation here. Starting off with NO2 minus to give N2 plus NO3 minus. So this one is a bit different because in this case, we have only one reactant, right? So the question is, how do we tackle this problem at the beginning? Because if you remember in the beginning stages of the previous examples, you have to separate the original equation into 2 half equations. So the question now becomes, how do we separate this into 2 half equations? And this is how you do it. NO2 minus to form N2 and NO2 minus to form NO3 minus. All right? So that's how you separate it. All right, basically you're starting with the same reactant on the left side for both half equations. All right, the products will be different, of course, for both half equations. And then you basically go through the steps like we did before. So first step is that we balance all atoms excepting oxygen and hydrogen, which in this case means you'd have to put a 2 here for the nitrogen. Here, we don't need to make any changes as far as the nitrogens are concerned because they're balanced. And then we balance the oxygens by adding, in this case, 4 water molecules on the right side, and in this case, 1 water molecule on the left side. And then we balance the charges, I'm sorry, not the charges, the hydrogens by adding hydrogen ions, which for the first half equation would mean adding 8 hydrogen ions. And for the second half equation, that would mean adding 2 hydrogen ions on the right side. And then we balance the charges, which would mean for this half equation, that's 8 minus 2, that's plus 6, and there's no charge here. So I'll add 6 electrons to the side. And for this equation here, let's see, we have minus 1, 2 minus 1, that's plus 1. So I would add 2 electrons to this side. And then to make sure the electrons are the same, what I would do is multiply this equation here by 3. So I'm going to end up with 3 H2O plus 3 NO2 minus to give 3 NO3 minus plus 6 H plus 6 electrons, right? So basically, you're going to add this equation to this equation. So to avoid confusion, I'm just going to put a line through this right here. And I'm just going to add these 2 equations together, which would mean that this 6 electrons will cancel out with this 6 electrons. These 6 hydrogen ions will cancel out 6 of these, leaving behind 2. And these 3 water molecules will cancel out 3 of these, leaving behind 1. So the final answer is going to be 2H plus, now here we have 2 NO2 minus and 3 NO2 minus on the same side. So that would be a total of 5 NO2 minus, right? And then on the product side, you're going to have nitrogen, N2, plus H2O, plus 3 NO3 minus. And that should be the final answer. But again, we need to check to make sure everything balances out. Starting with the hydrogens, we have 2 hydrogens here. We have 2 hydrogens, so that's okay. We have 5 nitrogens here. And we have 2 plus 3 nitrogens, 5. And then for the oxygens, we have 5 times 2, 10. And here we have 1 plus 9, 3 times 3, 9, 9 plus 1, 10. So the oxygens are balanced. And then as far as the charges are concerned, we have plus 2, minus 5, which gives -3. And over here we have -3. So the charges are balanced as well. So this would be the final equation, balanced equation. All right. So that's basically how that is done. Okay, any questions about that one? Any questions?
No questions.
All right. So that basically represents the end of chapter 4. The only other thing, let me see here. Let me scroll down. Right, the only other thing I want to talk about is this picture right here. This picture represents or is showing you what happens when we perform what is known as a redox titration. And basically what is involved is adding one substance to another in a redox reaction. And in this case, if I'm not mistaken, the substance that's being added from here is potassium permanganate, KMnO4. And inside here, if I'm not mistaken, this contains the oxalate ion. All right. So basically what happens, I don't know what the balance equation is. You can probably work it out, but I can write down the unbalanced equation. It's MnO4 plus C2O4 2 minus to give Mn2 plus CO2. All right. So you can probably, I will leave you to figure out what the balance equation is. Basically, you're going to go through the same steps as we did before. I just want to highlight that in this particular case, so what is happening is that you're adding this here to this. This is purple in color. Purple. All right, that's a potassium permanganate. And one of the products is the manganese 2+ ion, which is pink in color. All right. So basically what you're going to do is, if you were to do this experiment, is you're going to add the potassium permanganate to your solution containing the oxalate ion, and you continue to do that until this solution becomes pink. The solution in the flask here becomes a pink color. And when that happens, then you turn off the stopcock, and then you measure the amount of volume of the potassium permanganate added. And based on that, you can do calculations. For example, you can determine the percentage of the oxalate, or you can determine the concentration of the oxalate. It all depends on, the information that you're given in order to perform this experiment. So that's basically what this picture is showing you. Okay, so that's basically it for chapter 4. And what we're going to do right now is move on to chapter 5, which deals with gases. And again, a lot of what you learned in introductory chemistry, we're going to cover again in this chapter, plus some other things that you may not have met before. All right, so let's talk about gases and their behavior. All right. What are they like? Well, as you should know from before, gases are basically made up of very small particles that are highly energetic, and they're always moving around, and they're always bumping into the walls of the container and bumping into each other as well. And as a result of that aspect of the behavior of gases, in terms of the way gases behave in terms of what we can observe, we know that gases flow readily, and they tend to occupy the entire volume of their container, right? So we can relate that observation to the fact that the gas particles are highly energetic, always moving, and so on, all right? Now, at this juncture, I want to talk about a term that you may see from time to time, the term vapor, which is basically referred to a gas that is normally a liquid under room temperature and pressure conditions, all right? So we use the term vapor in association with substances such as water or methanol, because water and methanol under normal room temperature and pressure conditions exist as a liquid, but of course you can heat it and therefore vaporize these liquids to form the gas. So the gas is called a vapor. But other gases which exist as gases under normal conditions, we simply just call them gases. We don't call them vapors, all right? Okay, and what you'll find is that many low molar mass compounds can be easily vaporized or exist as gases under normal room temperature conditions, all right? And this list here is basically a list of different gases and their uses in industry. And just to highlight a couple of examples, acetylene, which is used for welding metals, carbon dioxide, which is used to manufacture sodas, carbonated beverages, because basically carbonated beverages like, Pepsi and 7-Up and Sprite and all of that is made up of a solution of carbon dioxide gas. Of course, you have flavorings and all of that, but basically that's what sodas are made of. Another example here is nitrogen, which is used in the manufacture of ammonia, and ammonia itself is used in the manufacture of fertilizers and plastics and so on, all right? So those are just a few examples of gases. So in order for us to understand how gases behave, we have to come up with a model that explains the behavior of gases at the microscopic level. And the model that we have now adopted, accepted, to explain these observations would be the kinetic molecular theory, all right? And basically, we kind of touched on it before. The theory basically says that the particles of a gas are highly energetic, always moving around, bumping into each other and bumping into the walls of the container. In fact, the motion of these particles are said to be translational. They tend to move in straight lines until they hit each other or hit the walls of the container, right? And when they hit the walls of the container, because of the force of that collision, then that collectively manifests what is called the pressure exerted by the gas on the walls of the container, right? So as stated here, the pressure that is exerted by a gas on the walls of the container is as a result of the collisions of billions, literally billions of gas molecules with the walls of the container, all right? And we're going to talk about that in more detail. And also, we can relate certain things that we observe with respect to the temperature, how gases behave when the temperature, for example, increases. We can relate that to the kinetic molecular theory as well, because according to the kinetic molecular theory, when you increase the temperature of a gas, you're imparting more energy to the gas particles. As a result, the gas particles will be moving around more rapidly, and they'll be colliding with the walls of the container more frequently and with greater speed, and therefore will exert a greater force on the walls of the container, and as a result, will exert a greater pressure on the walls of the container. So as stated here, the temperature is actually related to the average speed of the gas molecules, and we're going to discuss that in more detail later on as well. So one important property that gases actually exhibit is its ability to exert pressure on the walls of the container. So we're going to spend some time talking about what we mean by this term pressure. And this term in everyday language tend to be confused with force, but they're two different things, even though they're related. So here's the definition of pressure. Pressure is a force per unit area, all right? That's what pressure is. Now force, if you have done any physics, you know that force is basically a push or pull, right? So if I'm pushing on something, or if I'm pulling something towards me, then I'm exerting a force on that particular object. Well, pressure is the force that is exerted over a particular area, over or per unit area, all right? So that's the difference between pressure and force. And as such, based on the fact that pressure is equal to force per unit area, we can mathematically represent the relationship between pressure and force using this equation here, where pressure, in fact, let me see if I have it here. Okay, I don't have it here. So the equation would be pressure would be equal to the force divided by the area over which a force is transmitted. And therefore, based on this equation, we can figure out what the units of pressure is. Now, the SI unit of force is newtons, and the SI unit of area would be meters squared, which means that based on this equation setup, the units of pressure would be newtons per meter squared. And there's a special name given to this collection of units. It's called the Pascal unit, all right? Abbreviated PA, all right? So whenever you see Pascal, it means the same thing as newtons per meter squared, all right? And then, of course, that along with the normal metric prefixes, you can represent or express larger or smaller units of pressure. The most common one is the kilopascal, right? So kilo, we already know, kilo means 1,000. So 1 kilopascal is equal to 1,000 pascals. So those are the SI units of pressure. Now, there are some other units that we're going to talk about later on. We have what is known as the atmosphere unit, and then we have what is known as the millimeters mercury unit, which is the same exact unit, or in terms of value, as the torr unit. So millimeter mercury, torr, basically they're the same, all right? And I think the next slide has the relationship between all these different units. So here we have 1 atmosphere here, set being equal to all these values here. So 1 atmosphere is equal to 760 millimeter mercury, which is the same thing as 760 torr. And then we have some other units here. Now, to be perfectly frank, I do not anticipate us using this value, or this value, all right? The ones that we'll be more involved with would be the first 2 that are listed here and the last 3. The pascals, which is the same thing, by the way, as we said before, as newtons per meter squared, and kilopascals, right? So 1 atmosphere is equal to all of these here, all right? And we're going to talk about how the millimeter mercury unit was derived shortly. But it's important that you understand that these are the relationships between the 1 atmosphere and these different units, all right? So let's talk about how do we measure pressure? Well, it depends on what you're measuring. Now, there are 2 types of instruments we're going to talk about. The first one is known as a barometer. And the barometer is basically an instrument that is used to measure atmospheric pressure. As you should be aware, we on Earth, we basically are submerged on the surface of Earth under a mixture of gases. The main component would be nitrogen, which is about 78%. And then we have oxygen, which is probably about 20%. And then we have some other trace gases as well, right? So basically, as we walk around on Earth, we are actually experiencing the pressure of the atmosphere on our bodies, even though we do not feel it. So the instrument that we're talking about here that is used to measure the atmospheric pressure, as I said before, is called a barometer. And this is where we're going to get into the relationship between the atmosphere unit and the millimeter mercury unit. So the definition of the atmosphere unit is that 1 atmosphere is the pressure exerted by a column of mercury, which is 760 millimeters high, all right? So that's the relationship between the atmosphere unit and the millimeter mercury unit. And as I said before, the millimeter mercury unit is the same thing as a torr unit. And it turns out that 1 atmosphere is also equal to 101.325 kilopascals. So let me show you this, which is a setup for how we have defined the atmosphere unit in conjunction with the millimeter mercury unit. So here we have 2 setups. The first setup here on the left is a trough filled with mercury, and inside that mercury is inserted a tube. Now this tube is opened at both ends, right? So basically what will happen is that the atmosphere will exert a pressure here on the surface of the mercury outside the tube, and then you're going to have the atmosphere exerting pressure on the surface of the mercury inside the tube. So because the pressure here is equal to the atmospheric pressure here, that means that they'll be equalized. So therefore the mercury level here inside the tube will be the same as the mercury level on the outside of the tube. Now, the other setup here is identical to the first one, with the exception that the tube that is used here is sealed at one end, right? The other end is open, which is that end which is submerged in the mercury, all right? So the way this is put together is that you would have your trough filled with mercury, and then the tube itself here would be filled with mercury, and then the tube is inverted into the trough with the open end submerged. And if you wait a while, and if the tube is long enough, then what you'll find is that the mercury level will fall to a height of about 760 millimeters, right? And what this indicates is that whatever the atmospheric pressure that is exerted on the surface of the mercury outside the tube would be equal to the pressure that is exerted by this column of mercury at the same equivalent point, which is at the same level as the level of the mercury outside the tube, all right? So that's where the 760 number comes from in terms of the height of the mercury, which represents the height of the mercury, which will exert the same pressure as the pressure exerted by the atmosphere, all right? So that's why we end up with the pressure exerted by the atmosphere, that is called 1 atmosphere in this particular case. And that 1 atmosphere is going to be equal to 760 millimeters mercury, all right? So that's where we get that relationship from. And later on, this unit was also called the torr, named after the famous scientist from Italy, Torricelli, all right? So the torr unit and the millimeter mercury unit are both one and the same. Okay, so let's look at this simple example. The question is talking about a Canadian weather report, which gives atmospheric pressure as 100.2 kilopascals. So the question is, what is the pressure expressed in the unit of torr? Well, this is a very simple conversion problem. So basically, we're going to start off with 100.2 kilopascals, and we have to multiply by the appropriate conversion factor, where, let's see here, so 760 torr would be equal to 325 kilopascals. That's a relationship. And let me get my calculator here to do this computation. So 100.2 times 760 divided by 101.325. So according to my calculation, this works out to be equal to 751.6, and the units will be torr. And that's it, all right? So pretty much similar to other types of conversions that we have done. The only difference is that we're working with different units of pressure. Okay, so let's talk about another instrument that is used, but this time we use this instrument to measure the pressure of a gas which is trapped in a container. And this instrument is called the manometer. And as stated here, the manometer is used to measure the pressure of a sample of gas. And what is used, actually, as you're going to see in the diagrams on the next couple of slides, is that the pressure is measured, the pressure of the gas, that is measured by looking at the difference of the heights of the mercury or other liquid, but mercury is a liquid of choice, which we're going to explain why mercury is a liquid of choice for these types of instruments, right? In the two arms of the manometer. So what we're talking about is something looking like this. Now, this particular setup here is, or this schematic diagram here is representing what is known as a closed-end manometer, right? So basically, it consists of a tube, a U-shaped tube. One end is closed right here, which contains mercury, right? And the other end is connected to your container, which has the gas that you're trying to measure the pressure of. So you turn on this tap right here, the gas flows through, and it exerts the pressure on this end, on the surface here. And that means that this liquid level on the other side will be pushed up. And it turns out that well, for one, there's no gas right here. So here is effectively a vacuum, all right? And as a result, there's no pressure that is being exerted here on the surface here. So therefore, what we can conclude is that the height difference here between the two mercury levels on either sides of the U-shaped tube would be equal to the pressure of the gas that is exerted right here, right? So the pressure can be expressed in terms of the millimeters of mercury that is measured as the height difference between here and here, all right? And that's it. That's basically how this instrument works. So in this case, when you measure the height difference here, you can simply quote that as the pressure exerted by the gas expressed in millimeters mercury. Now, that is true if mercury is the liquid that you're using here. Now, if you're using other liquids, and this also applies to mercury as well, to calculate the pressure expressed in pascals, then you'd have to use this equation right here, all right? So let me explain what this equation is all about. So according to this equation, the pressure is equal to G, which is a constant known as the acceleration due to gravity, times D, which is the density of the liquid expressed in kilograms per meters cube, times H, which would be the height difference between the two mercury levels on either side, and that would be expressed in meters, all right? So basically, if you plug the numbers into this equation here, then you're going to get the pressure expressed in pascals, all right? So that's basically how a closed manometer works. Now, the next slide shows you a different type of manometer where one end is open to the atmosphere and the other end is connected to the container which has a gas, all right? So we have two situations here. I'm going to try to explain what's happening in both situations. So in this particular situation, where the gas is allowed to flow through and exerts its pressure here, and then on this end, the atmosphere will exert its pressure here, right? So the pressure exerted by the atmosphere here is called the atmospheric pressure, or it's also called in some textbooks, the barometric pressure. And that's why you have P bar right here, right? So you'll notice that the mercury level here is lower compared to the mercury level here. What that tells us is that the pressure exerted by the gas here would be greater than the barometric pressure. And the difference between those two pressures will be equal to the delta H, which is the height difference between the two mercury levels on either side. So therefore, we can write down a relationship between the pressure of the gas, the delta H, and P bar. And that is that the pressure of the gas would be equal to P bar plus delta H. And that's what we have here. All right. So that's the relationship between the pressure of the gas, the barometric pressure, and delta H. All right. So to calculate the pressure of the gas, we need the barometric pressure, which we can get from the barometer, which we talked about earlier. And then, of course, if we measure delta H here, then we simply add delta H to P bar, and that gives us the pressure of the gas. So that's what happens in this case. Now, on the other side, you'll notice that the P gas here, or the mercury level here, is higher on this end compared to this end. So what that tells us is that the barometric pressure here is greater than the gas pressure here, and the difference between those two values will be delta H. So therefore, we can write down that the relationship between the barometric pressure and the pressure of the gas would be P bar plus delta H gives you P gas, which is what we have here, right? P bar is equal to P gas plus delta H. And therefore, if you want to find the pressure of the gas in this case, let me write this down here. Let me see here. Okay, so P gas will be equal to P bar minus delta H. All right, so basically all we have to do to find the pressure of the gas in this case is to measure delta H and subtract it from the barometric pressure, and that's it. All right, so that's basically how the open-end manometer works. Okay, so before we leave this slide, I want to answer this question here. It says, what is the pressure of the gas if delta H is 100 millimeters and P bar is 760 millimeters? Well, that's very simple. Based on what this equation I just mentioned, that means the answer here is that the P pressure of the gas, let me squeeze that in somewhere here. Let me put that right here. So the pressure of the gas in this case would be equal to P bar, which is 760 millimeter mercury, minus 100 millimeter mercury. So that would be equal to 660 millimeter mercury, and that's it. All right. So that's basically how the open-end manometer works. Okay, now let me see how much time do we have for the next break. Okay, I should be able to explain this, okay, in the time that we have left. Okay, so this example right here, and please forgive the scribblings. I recorded a video with this, so I forgot to erase these writings that I have here. But I'll leave it up here because this is actually showing us the solution to the problem. So this particular question here illustrates why it is that mercury is a liquid of choice when it comes to instruments such as the barometer or the manometer. All right, so the question says, calculate the height of a column of water, and it gives a density which is 1.00 grams per cm cube, that exerts the same pressure as a column of mercury, where the density is 13.6 grams per cm cube, 760 millimeters high. All right, so basically what the question is asking for you to calculate is the height of the water column that will exert the same pressure as a column of mercury, which has a height of 760 millimeters, right? Now remember, 760 millimeters mercury is equal to 1 atmosphere. So that would be the atmospheric pressure, right? Okay, now if you recall, I showed you this equation right here, which gives you the pressure exerted by a column of liquid. The pressure is equal to the height of the column times the acceleration due to gravity times the density of the liquid, right? So what I'm going to do is basically apply this equation for both water and mercury. The pressure exerted by the column of a column of water and the same pressure exerted by the column of mercury, right? So this is the first thing I'd write on here. The pressure of the column of water would be equal to the pressure of a column of mercury. And what I would do now is basically express these terms in terms of this equation right here. So for the pressure exerted by a column of water, that would be equal to the height of the water column times G times the density of water. And then for the mercury, that would be equal to the height of the mercury column times G times the density of mercury. All right. Then what I would do is cancel out the acceleration due to gravity because it's the same on both sides. And then what I would do is divide both sides by the density of water, because what I'm trying to end up with on one side here is the height of the water column, right? So this here will cancel out with this, and I'm going to end up with this expression right here. The height of the water column will be equal to the height of the mercury column times the density of mercury times, I'm sorry, not times, divide the density of water. And then I'll plug the numbers in, and this is what I end up with. 760 millimeters times 13.6 divided by 1.00 grams per cm cube. So when you work that out, that works out to be equal to 10,300 millimeters, all right, of water. So let me put millimeters here as the units, right? Okay, so 10,300 millimeters, that is basically the same thing as 10.3 meters. So what this is suggesting is that if you were to use water instead of mercury for instruments, let's say, for example, the barometer, right? If you, instead of using mercury, you're going to use water, then you're going to need a tube which is at least 10.3 meters long in order for you to use that as an instrument to measure the atmospheric pressure, right? And just in case you don't know what 10.3 meters look like, I don't know how many of you, well, I know one of you guys have met me before, and you'll know that my height is about, I'm just under 6'5", right? 6'5" is just about 2 meters, slightly less than 2 meters, right? Now, the tube that would be required for water would be 5 times my height, in other words, all right? And as you can imagine, that would be very inconvenient in terms of being a useful instrument for measuring atmospheric pressure. And that is a reason why liquids such as water is not used in these instruments. In fact, mercury is used, even though it's more expensive, it's much more expensive, but in the case of mercury, you need a smaller tube. The tube would have to be at least 760 millimeters, which is less than 1 meter, all right? So that's the reason why mercury is a liquid of choice, and other liquids, such as water, will not work for practical reasons. And this is mainly due to the fact that mercury has a relatively high density of 13.6 grams per cm cube. So because of the high density of mercury, the length of the tube required will be relatively small compared to water, whose density is less. right? And therefore, the length of the tube required would be longer. Okay, so I hope that clears up why mercury is a liquid of choice when it comes to instruments such as the barometer or the manometer. Okay, I'm going to take a break here before we get into a discussion of the different laws governing the behavior of gases. All right, so we're going to take another 10-minute break, and then we'll get back here to continue our discussion of gases.
Okay.
All right. Okay, can you hear me? Hello, can you hear me?
Yes, I can hear you.
Oh, okay. Oh, it looked like your other colleague left. All right. So for the time that we have here remaining, we're going to talk about the different laws that govern the behavior of gases, all right? And the first law we're going to talk about here is Bohr's law. And Bohr's law, as you can see stated here, describes the relationship between the pressure of a gas and its volume. Okay, why is this thing not responding? Hold on 1 minute. Let me try. Okay, so this is what the law says in words. For a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure. All right. So that's one way of stating it. Another way of stating it is that for a fixed amount of gas at a constant pressure, a constant temperature, the product of the pressure and the volume is constant. All right. So basically, those are two ways of stating Bohr's law. Now, mathematically speaking, we can state it this way. PV is equal to a constant. P is the pressure, V is the volume, and the product of the pressure and the volume is equal to a constant. Or, and this is actually a more useful way of stating it, P initial times V initial is equal to P final times V final. All right. I prefer to use, since I'm a bit lazy, I prefer to simply restate this as P1 V1 is equal to P2 V2. All right. It's the same thing. All right. So P1 and V1 would be the initial pressure and volume, and P2 and V2 would be the final pressure and volume. All right. So this is a more useful expression of Bohr's law, because we can actually use this relationship to solve for one of these items if we know the value of three of the other items. So for example, if you want to find, let's say, P2, then all we have to do is rearrange this to get P2 is equal to P1 V1 over V2. All right. And that's basically how we use Bohr's law to solve problems like that. All right. So this slide here basically shows you the graphical relationship or representation of the relationship between pressure and volume. Now, this graph here on the left is a plot of pressure versus volume. And as you can see, as the volume increases, the pressure decreases. All right. So as you increase the volume from V to 2V, so if you double the volume, what happens to the pressure? The pressure is reduced by a similar factor. It's halved from 4 atmospheres to 2 atmospheres. And then if you were to double the volume again from 2V to 4V, the pressure is halved from 2 atmospheres to 1 atmosphere. So that basically shows you how the volume varies with pressure. Now, the graph that is shown on the right is a plot of 1 over the pressure versus volume. And as you can see, it's a straight line relationship. And one can see that because, let me get out of this here. I think I'll do a better job if I show you here. Let me get rid of it. Okay, so remember, one way of expressing Bohr's law is PV is equal to a constant, right? Or we can express this as K times 1 over P is equal to V, or we can express this as 1 over P is equal to 1 over K times V, which is equal to K prime, which is another constant, times V. So K prime here is the same thing as 1 over K. So if you plot, according to this equation, if you plot, so 1 over P will be equal to K prime times V. So if you plot 1 over P versus V, you're going to get an equation of a straight line where the slope would be equal to K prime right here. So this would be the slope, right? So this is going back to stuff that you should have learned in math, all right? Okay, so let me go back to the PowerPoint here. And that's basically explaining what I just did, explains the shape of this graph right here, the reason why it's linear, all right? Okay, so this question says, estimate the pressure at 3V and at 5V. Which plot is easier to use for making this information? Well, generally speaking, when it comes to estimations of this type, it's easier to use a straight line relationship as opposed to the curve. So in other words, if we were to estimate what the pressure would be at 3V, excuse me, well, 3V would be about, hold on, let me see, about here. So all you have to do is just draw a vertical line, and I'm going to do my best in doing that. So that's 3V, and then you draw a horizontal line to intersect with that. So this looks like about, I don't know, 0.75, and that would be equal to 1 over P. So 1 over P is equal to 0.75, which would mean that P would be equal to 1 over 0.75, which would be the same thing as 4 over 3, which would be the same thing as 1.33 atmospheres, all right? And that's basically how you can determine the pressure at 3V, and you should be able to do the same thing at 5V. Actually, 5V would be about here. So again, you do the same thing, you draw a line here, this, and then the vertical line, I mean a horizontal line across like this. So that looks like 1.5. So 1 over P is equal to 1.5. So therefore P is equal to 1 over 1.5, whatever that gives. 1 divided by 1.5. And according to my calculation, that would be 0.67 atmospheres. Okay, so that's just answering. What I just did is an answer to the question in this green box right here. All right. Okay. So let me get out of this here and move on to the next. So the next slide is a question based on Bohr's law. So the question says you have a helium party balloon with a volume of 4.50 liters, where the atmospheric pressure is 748 torr. So it says, assuming that the temperature remains constant, what will be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? So when you're given a question of this type, it's very important that you identify the different terms. Now, remember, the equation that we'll be using in this case is P1 V1 is equal to P2 V2, all right? So you need to identify the different terms, what's P1, what's V1, and so on. So let me get this out of the way here. Okay, so the first thing I notice here is they gave the initial volume, which is V1. They gave the initial pressure, which is P1, and they gave the final pressure, which is P2. And this information here is basically irrelevant, so we can ignore that. And the question is asking for V2. So we have to rearrange this equation to solve for V2. So V2 would be equal to, you know what? Let me get out of this here and use my writing, software, because I hate when my, okay, so let me clear this up. All right, so let's see if I can find the question over here. Okay, so again, as I was saying, the equation is P1 V1 is equal to P2 V2, right? And according to the question, V1, well, the question is asking for P2. I'm sorry, the question is asking for V2. So V2 will be equal to P1 V1 over P2. And all you have to do from here is plug the numbers in. So according to the question, the initial pressure is 748 torr. The initial volume is 4.50 liters. And the final pressure, P2, is 557 torr. So let's see what the result will be. 748 times 4.5 divided by 557. And according to my calculations, this works out to be equal to 6.04 liters. And of course, the torr units will cancel out. So that would be the final answer. All right. So that's a relatively simple application of Boyle's law. Now, before we leave this, I just want to point out one thing about using Boyle's law, and that is that it doesn't matter what the units are for pressure and volume on either side. However, the units of P1 and P2 must be the same. So P1 and P2 must have the same units. And the same is true for V1 and V2. V1 and V2 must have the same units, right? And that's important because you may be given a question where, for example, P1 is in atmospheres and P2 is in, let's say, millimeters mercury. So what that means basically is that before you can use the Boyle's law equation here, you either have to convert the atmosphere's units to millimeters mercury for P1 or convert the millimeter mercury units to atmospheres before you can plug the numbers into that equation. All right? So that's something that you need to keep in mind. The units have to be consistent on both sides of the equation. Okay, any questions about this particular example? Any questions? Any questions? Okay. Let me go back to the PowerPoint here. All right, so the next law we're going to talk about is Charles' law. And Charles' law describes the relationship between the temperature of a gas and its volume. And basically, in words, the law says that the volume of a fixed amount of gas at a constant pressure is directly proportional to its Kelvin temperature. And the Kelvin temperature is also known as the absolute temperature, which we'll talk about in more detail later on. Why is it that the Kelvin temperature is a specific unit that we have to use here in this law? All right. In fact, the next line here talks about the concept of absolute zero, which is a temperature that is obtained when you extrapolate the graph that we're going to talk about later on to zero volume. And this represents the kinetic energy at which the gas molecules, or I should say, this represents the temperature at which the gas molecules have no kinetic energy, right? So the absolute zero value on the Kelvin scale is the same thing as minus 273.15 degrees Celsius. So 0 Kelvin is equal to that. And this is showing you how the Kelvin scale comes about. And it comes about as a result of basically what we observe in Charles' law. So what this is showing you here is a plot of volume versus a temperature. Volume versus a temperature. And the temperature is expressed in Celsius for a gas. So as you reduce the temperature, the volume decreases. Obviously, that's what you'd expect, all right? Now, what you'll find is that for most gases, of course, if you cool the temperature, if you cool its temperature to a low enough value, it becomes a liquid. And therefore, it doesn't behave as a gas anymore. And therefore, we cannot do any more plots to examine how a gas would behave below that temperature of liquefaction. So what was done was that this line would be extrapolated to see where it would cut the x-axis. And it turns out that it will cut at about 273 degrees Celsius, minus 273 degrees Celsius. And what that represents is where if the gas were to exist as a gas at a low temperature, at these low temperatures, then the volume will contract to about 0, right? And that represents basically where the particles will have absolutely no form of translational, rotational, or vibrational energy. In other words, has no kinetic energy whatsoever. And that is what is called absolute zero. So that's where the Kelvin scale comes from. Basically, what was decided by the powers that be, that where the line cuts the x-axis, that is defined as absolute zero. So let me indicate that here. So this here is defined as absolute zero, right? Expressed in Kelvin, all right? Which is basically shown right here, all right? So as a result of that, 0 Kelvin has been set to be equal to minus 273 degrees Celsius, which means that 273 Kelvin would be equal to 0 degrees Celsius. So in other words, the relationship between the Celsius and the Kelvin unit would be that the temperature in Kelvin is equal to the temperature in Celsius plus 273 Kelvin, all right? Okay, so that's basically showing you Charles' law and how it works. Now, let me just say this, which I unfortunately don't have here. So let me write it here. Mathematically speaking, we can express Charles' law this way. V1 over T1 is equal to V2 over T2. But in this case here, it's the amount of gas that is fixed along with the pressure. So the amount of gas and the pressure would have to be constant in order for this law to hold true. And very important, T1 and T2 must be expressed in Kelvin, right? So the temperatures that are used in that law must be expressed in Kelvin. Okay, so based on that equation, we can look at this problem right here. Question says, for a balloon where the temperature indoors would be 27 degrees Celsius, the volume is 2.0 liters. What will be the volume outdoors where the temperature is minus 23 degrees Celsius? And it says assume no change in the gas pressure. So in this case here, what we're going to do is write down the mathematical expression for Charles' law, which is V1. You know what? Let me go back to my writing software again. Let me open this here. Okay, so the equation we're going to use here is V1 over T1 is equal to V2 over T2. What this question is asking for is V2, so V2 will be equal to V1 over T1 times T2. And then we put the numbers in. So V1 is the initial volume, which is 2.00 liters, times the final temperature. Now, T2 is equal to minus 23 degrees Celsius. We have to add 273 to that to get the corresponding Kelvin value, which would be 250 Kelvin. So here we're going to multiply by 250 Kelvin. And then we're going to divide by T1, which is 27 degrees. So T1 is equal to 27 degrees Celsius plus 273, which would be equal to 300 Kelvin. So that goes here. And then we do our number crunching. So 2 times 250 divided by 300. So according to my calculation, this works out to be equal to 1.67. And because the Kelvin units cancel out there and there, the final answer will be in liters, all right? And that's basically how that is done. Okay, any questions about this? Any questions? Are you there? Okay. All right, so what's next? So the next law we're going to talk about is Avogadro's law. And this law describes the relationship between volume and the moles of a gas. And it says at a fixed temperature and pressure, the volume of a gas is directly proportional to the number of moles of the gas or the number of molecules of the gas. All right. So there are several ways of expressing this law mathematically. Volume is directly proportional to n, or volume is equal to a constant times n, or volume over number of moles equal to a constant, or another way of expressing this would be, let me squeeze this up here. V1 over N1 is equal to V2 over N2, all right? So this is yet another way of expressing Avogadro's law. And at this juncture, I want to introduce to you, or I should say reintroduce to you, the concept of standard temperature and pressure, SDP, which is important because in order for you to make meaningful comparisons between different gases, we have to, in some cases, in a lot of cases, keep the temperature and pressure constant. So what was decided was that one atmosphere would be defined as the standard pressure, and 0 degrees Celsius, which is the same thing as 273 Kelvin, would be defined as the standard temperature. And then another term that I need to reintroduce to you is the term molar volume, which is basically the volume occupied by 1 mole of a gas. And one can actually prove, which we're going to talk about later on, that under standard temperature and pressure conditions, STP conditions, the molar volume of an ideal gas is going to have a volume of 22.4 liters. In other words, for 1 mole of any gas, the volume occupied under standard conditions of temperature and pressure would be 22.4 liters, all right? So that's Avogadro's law. And then the next law is Gay-Lussac's law, which talks about the relationship between pressure and temperature. And basically, this is what the law says in words. At a fixed volume of gas and moles of gas, the pressure of a gas is directly proportional to the temperature expressed in Kelvin. And these are the different ways of expressing it. And then there's one way of expressing it, again, which is more useful, and that is P1 over T1 is equal to P2 over T2. Again, the temperatures must be expressed in Kelvin. T1 and T2 must be expressed in Kelvin. Okay, so let me go back to my pointer here. All right, so let's look at this example. This question says, calculate the volume of occupied by 4.11 kilograms of methane gas, CH4 at 22, at STP, I'm sorry. Okay, so let me get out of this here and go to my writing pad here. And the question gives us 4.11 kilograms of methane, and it's asking for you to calculate the volume in liters at STP. So the first thing I would do is convert the 4.11 kilograms of methane to grams of methane. So you're going to have 1 kilograms of methane down here, 1,000 grams of methane above, and then the next conversion factor will be converting from grams of methane to moles of methane. And the way we do that is you're going to have 1 mole of methane above and the molar mass of methane below, which is, let me calculate that here. So in the case of methane, which is CH4, the molar mass would be 16.05 grams. And then the next conversion factor is where the STP conditions would play an important role, because remember we said that under STP conditions, 1 mole of any gas will have a volume of 22.4 liters. So here I'm going to put 1 mole of CH4 below and 22.4 liters of CH4 above. And then do the number crunching. So 4.11 times 1,000 divided by 16.05 times 22.4. And according to my calculations, this works out to be equal to 5,740 liters of methane. And that's basically how that is done. Okay, any questions about this example? Any questions? Okay. All right. So let me see what's up next. Okay, so far we have talked about the different laws here, which is summarized on this screen right here. All right. This is Boyle's, this is Charles, this is Avogadro's. So basically we can combine these laws to get what we call the combined gas law, which is simply this right here. P1V1 over N1T1 is equal to P2V2 over N2T2. And again, we can use this to solve problems where you need to find one if you don't know what the others are. Put the numbers in, manipulate the equation accordingly, and you'll get your answer depending on what the question is asking for. Okay, I think this is going to be the last example I'm going to work. So let me deal with this. So this question talks about 2 flasks, or actually the same flask containing oxygen. Over to the left, the flask is placed in an ice bath. Over to the right, the flask is placed in boiling water. And the question says, what is the pressure for the flask on the right? So let me go to my writing software here. Okay, so basically, let's see what we have here. It says STP, so standard temperature and pressure, for the one on the left. So that means that T1 is equal to 273 Kelvin, and P1 would be equal to 1.00 atmospheres. And the one on the right, let me see what it says. T2 would be equal to 100 degrees Celsius, which is 373 Kelvin. And P2 is what the question is asking for. So the combined gas law is P1V1 over N1T1, which is equal to P2V2 over N2T2. Now the thing is that the volume is the same, so V1 and V2 will cancel out, and the amount of gas will be the same, so N1 and N2 will cancel out. So therefore, this would be simplified to P1 over T1 is equal to P2 over T2. And then to solve for P2, that would be equal to P1 over T1 times T2. And then we put the numbers in. So that will be 1.00 atmospheres times T2, which is 373 Kelvin, divided by 273 Kelvin. And so that's 373 divided by 373 divided by 273. Okay, so according to my calculation, this works out to be equal to 1.36 atmospheres. And that's how that is done. All right. Okay. So what I'm going to do is I'm going to stop here. And the next time we get together, which by the way will be next week this time because Monday is a holiday. So the next time we get together, we'll be talking about the ideal gas law. All right. Let's see. Okay, so that's it for today. And I'll see you guys on Wednesday of next week. All right, until then, take care.